In this video, we'll dive into key manufacturing techniques and strategies that shape modern production, from precision measurement in metrology to innovation of lights out factories. Each topic highlights the importance of accuracy, efficiency, and reliability in today's manufacturing world. Design for Assembly DFA is a design approach focused on simplifying the assembly process of a product, often by minimizing the number of parts and ensuring that components fit together with ease and efficiency. DFA encourages the integration of parts and uses use of features like snap fits, which help reduce manufacturing and assembly time, lower production costs, and improve reliability by eliminating unnecessary components and fasteners. This approach is widely applied in industries like automotive, electronics, and consumer goods, where ease of assemblies and cost efficiency are critical. DFA is particularly important because it emphasizes simplicity and functionality in design. I enjoy working with DFA because it challenges designers to think critically about each component's role in the final product, incorporating snap fits and other built-in assembly aids exemplifies the innovation possible in simplifying complex assemblies. This process doesn't just save time and resources, it can also significantly improve the user experience and product longevity by reducing potential failure points. Capabilities: DFA can reduce costs by minimizing assembly labor and part count, leading to faster production times. It often results in more robust products that are easier for end users to disassemble, maintain, or repair. This can lead to higher customer satisfaction and potentially lower warranty costs. DFA can sometimes constrain design freedom, especially in products where functionality requires complex interactions between parts. Additionally, while reducing parts can improve assembly, it might increase the manufacturing complexity of individual components, sometimes leading to a need for specialized processes. Metrology is the science of precise measurements, which is foundational in engineering and manufacturing. It ensures that every component meets strict specifications, allowing for parts to fit together perfectly and perform reliably. Without accurate measurements, even the best designed parts could fall short, causing issues in assembly and compromising performance. Metrology plays a critical role across various industries, for automotive and aerospace to medical devices, where a huge degree of precision is required. In manufacturing, metrology is applied at multiple stages. During production, it's used to verify that parts meet design specifications, ensuring quality and consistency. In quality control, metrology confirms that finished products are within tolerance, so they're safe, reliable, and perform as expected. For instance, in the aerospace industry, where exact dimensions are crucial for safety, metrology allows manufacturers to confirm that each component meets stringent standards before it even ever enters the field. Metrology stands out to me because it encompasses such a wide range of devices and methods for measuring components, each tailored to specific tasks, for using calipers and micrometers for measuring small distances to advanced coordinate measuring machines and laser scanners for complex shapes. The tools are incredibly varied. It's fascinating how metrology dives into the details, often requiring specialized techniques to achieve precision. What's also intriguing is the concept of measuring devices. Metrology itself has high standards and accuracy must be constantly verified. Tools and machines used for measurement need to be calibrated regularly, often against even more precise instruments. This recursive quality of metrology, where measuring devices are validated by devices, ensures that every tool in the production line is performing at its peak accuracy. This process is essential, especially for manufacturing at scales where even the smallest variation can lead to a significant difference in performance. Metrology allows manufacturers to achieve high tolerances, which is essential in industries like aerospace, automotive, and medical devices. Its precision ensures that each component performs as intended, whether in surgical instrument or a jet engine part. With the advancement of technologies, modern metrology tools can now measure down to the micron level, allowing engineers to detect the smallest inconsistencies and make precise adjustments to improve quality. Limitations. Despite its benefit, metrology faces some challenges. Environmental factors such as temperature, humidity, and even slight vibrations can impact the accuracy of measurements. Huge precision tools like CMMs require controlled environments, which can be expensive to maintain. Additionally, achieving high levels of precision can be both time consuming and costly, as some devices are sensitive and need specialized operators. Destructive manufacturing techniques are testing methods that involve pushing materials, components, or even entire assemblies to the point of failure. This testing isn't about damaging parts without purpose. It's a controlled process that gives designers and engineers a clear picture of how and when failures occur. In high-stakes industries like aerospace and automotive, destructive testing is critical for ensuring that components can handle extreme scenarios. I find destructive testing particularly interesting because it focuses on uncovering the limits and vulnerabilities of design. When I worked at Pratt& Whitney on jet engines, destructive testing was a routine part of validating engine components. They conducted some intense tests, including setting off charges inside engines to assess how they react to explosive forces. Another memorable example was bird strike testing, where they literally simulate birds colliding with jet engines by launching real frozen birds into them. Uh, these extreme tests are done to ensure that the engines can handle unexpected impacts without catastrophic failure. In critical fields like aerospace, these tests aren't just about ensuring performance, they're about safeguarding lives by making sure each component can withstand real world challenges. Destructive testing is one of the most effective ways to evaluate the true strength, durability, and safety of component. It reveals hidden weaknesses and helps refine materials, shapes, or structural component or structural supports to make a product as safe and reliable as possible. For products used in high stress environments like aircraft, cars, and heavy machinery, destructive testing is often mandatory to meet safety and regulatory standards. The major limitation of destructive testing is cost, since these tests destroy the product each time it is essentially lost, which can be expensive, especially testing complex or high value components like jet engines. Moreover, simulating every possible failure scenario is often impractical, so there is a chance of encountering unexpected issues in the field. Deburring is a finishing process used to remove small imperfections known as burrs from edges of machine parts. These burrs are tiny, sharp edges or pieces that can form on metal during machining or cutting processes. While they might seem insignificant, burrs can cause issues if left on the part, affecting everything from fit and assembly to safety and performance. I believe deburring is crucial because it directly impacts the quality and functionality of a finished part. When I was working at Pratt& Whitney, I was part of the deburring process on engine blades, where precision and smooth edges are critical. We use wire brushes to carefully deburr the blades, ensuring no burrs or rolled edges were left. This attention to detail was especially important for the next step, shot peening, a process that strengthens the material by blasting it with small hard particles. If the blades had any remaining burrs or rolled edges from machining, it could interfere with the shot peening process, potentially weakening the blade instead of strengthening it. This experience highlighted how vital deburring is for maintaining the quality and safety of a component. Deburring ensures that parts meet precise specifications, help eliminate sharp edges that could interfere with assembly to create safety hazards. In addition to improving fit and function, deburring also enhances a part's aesthetic appeal by creating smooth, clean edges. Deburring can be a labor-intensive process, especially when done manually. Additionally, achieving uniform results can be challenging as some materials and shapes are harder to deburr effectively than others. Certain deburring methods like abrasive blasting can also be costly or require special equipment. Computers have transformed manufacturing, bringing unprecedented levels of precision, efficiency, and control to the production process. From robotic arms to complex computer-controlled machinery, automation allows manufacturers to achieve high quality results with less human intervention. I find the concept of computers in manufacturing fascinating, especially the idea of lights out factories. These are production facilities designed to operate autonomously with a with minimal or no human intervention. Once the machines are set up, they can run 24/7, allowing companies to maximize productivity without continuous oversight. In a lights out factory, CNC machines, robotic systems, and other automated equipment work together to keep production moving without interruption, creating a highly efficient and scalable manufacturing environment. This approach is valuable in reducing labor costs and eliminating downtime, making it ideal for large-scale manufacturing where consistency and efficiency is key. Uh, computer is Computer in manufacturing enable unmatched precision and repeatability, essentially for producing high-quality components. Technologies like CNC and adaptive control allow machines to make complex cuts and adjustments, automatically minimizing errors and improving speed in lights out factories. Automation enhances productivity by enabling round the clock operators without the need of continuous labor. While automation has many benefits, it can be expensive to implement with high upfront costs for machinery and software. Thanks for watching. I hope this overview provided insight into the tools and techniques that drive manufacturing forward, whether it's measuring with precision or pushing components to their limits. Each method plays a critical role in creating quality parts.